Imagine standing next to a jet engine at full throttle. The roar is 140 decibels, loud enough to vibrate your very bones. Usually, to stop that sound, you need a massive, heavy concrete wall. But here is the problem. If you block the sound with a wall, you also block the air. In engineering, there has always been a brutal trade-off between silence and ventilation. You can have one, but rarely both. Until now. In February 2026, researchers at HKU and Cambridge published a breakthrough that defies common sense. They created a material that is literally mostly empty space, yet it stops sound dead in its tracks.
This isn't just a better muffler, it's a fundamental shift in how we manipulate physics. It relies on a concept called duality symmetry, a mathematical balance that was thought to be nearly impossible to achieve in hardware. Think of it like a mirror for physics. By perfectly balancing the way a material responds to pressure and the way it responds to velocity, you can create a trap for energy that doesn't require a physical barrier. The result is a structure that looks like a high-tech honeycomb, but acts like a black hole for noise. It's one of those things that seems simple until you see the math behind it.
To understand why this is so clever, we have to look at how sound actually travels. It's just a pressure wave moving through air molecules. If you want to stop it, you usually have to absorb that energy as heat, but absorption is bulky and inefficient. The HKU team took a different approach. Instead of absorbing the sound, they used the geometry of the material to make the sound fight itself. This is the duality part. By matching the acoustic impedance of the material to the air itself, the sound wave enters the structure without reflecting, only to be trapped in a geometric maze. The researchers found that by arranging these traps in a specific symmetrical pattern, they could exploit the duality of the wave's components. This forces the sound into a loop where it cancels itself out entirely. And because the traps are located on the sides of the channels, the center remains completely open. It's like having a window that lets in the breeze but leaves the city noise outside. The engineering behind this is absolutely brilliant. They've solved a problem that has plagued acoustics for over a century, and they did it using nothing but the power of pure geometry.
But wait, if it's just geometry, why haven't we built this before? The answer lies in the scale. These structures are so small and so complex that they were impossible to manufacture until very recently. We are talking about features thinner than a spider silk, arranged in 3D patterns that would make an architect dizzy. To build this, you need the most advanced manufacturing tech on the planet. In the next module, we're going to look at the impossible manufacturing process, from nanolithography to 3D printing, that brings these silent structures to life.
To build a metamaterial that exploits duality symmetry, you have to work at the scale of sound itself. For high-frequency noise, that means creating structures measured in micrometers. The geometry isn't just a simple hole, it's a unit cell, a repeating block that contains a series of nested resonators. Think of it like a Russian nesting doll, but for sound waves. Each of these resonators is tuned to a specific frequency. When sound hits the cell, the resonators vibrate in a way that creates an equal and opposite wave, canceling the noise before it can pass through. This is where the duality comes in. In a standard material, sound waves change speed as they enter. But in this metamaterial, the geometry is designed so the effective density and effective bulk modulus are perfectly matched. When these two properties are equal, the material becomes transparent to the wave's entry, but opaque to its exit. The sound goes in easily, but it can't find its way out. It's a one-way street for energy. To achieve this, the researchers used a technique called nanolithography. This is the same technology used to make the world's most advanced computer chips. But there's a catch. Nanolithography is usually flat, 2D. To trap sound, we need 3D depth. This required a new process called two-photon polymerization, or 3D nanoprinting. Imagine a 3D printer nozzle that is smaller than a single bacteria. It moves with incredible speed, building the complex internal lattices layer by layer, atom by atom. The precision required is staggering. If a single strut is off by just a few nanometers, the duality symmetry breaks and the sound just leaks right through. The researchers also had to solve the problem of material strength. Most 3D printed nanostructures are incredibly fragile. They behave more like a wet noodle than a piece of engineering hardware. To fix this, the HKU and Cambridge team used a hybrid approach. They printed the 3D skeleton and then coated it with a thin layer of nickel using a process called electrolysis plating. This created a metamaterial ceramic, something that is as light as air but as stiff as steel. It's the perfect material for high-stress environments like jet engines.